Welcome to my presentation on ME4005 Lab 3 beam vibration. Overall, the outline is very similar to report. You have the objective, the setup, the results, then the conclusion. First, for the objectives, we want to perform a free vibration experiment of a cantilever beam. We want to then utilize the strain gauge and connect it to a quarter Wheatstone bridge to turn output strain into voltage. Then we want to take that collected voltage and perform a spectrum analysis and all these other plots analyses so that we can figure out the damping ratio, the natural frequency, and the damped natural frequency, and the sensitivity of all of it. First, for the experimental setup, Lab 3 is very similar to Lab 2, the quarter Wheatstone bridge connected to a strain gauge on a cantilever beam. We want to utilize the Wago snap connectors at 120 ohm resistors. The strain gauge is connected to the fourth quarter, where the other three are the three other 120 ohm resistors. We connect this to the TI MSP432. It reads the output voltage, but also provides the input, which is a little bit more than 5 volts. Connect this MSP432 to your laptop. Make sure your phone or your charger is not plugged in, your phone is farther away, so you have less noise. Use the high-speed DAC as it's just way more accurate. It's way better than just the normal speed DAC. Sampling rate, at 2000 hertz, the buffer of 15,000 samples, so 7.5 seconds. Data, this gives precise readings. From the small changes, the very small changes in a strain gauge, which is what a strain gauge gives. The cantilever must be clamped to the table, give about 9 inches length of the vibrating length. So from the tip to the fixed end of the actual vibration length is 9 inches, not 12. Then for the cases 1 through 4, cases 1, 3, and 4, you all take your finger and you displace the ruler by 20 millimeters or 2 centimeters. With a coin, you raise a quarter 4 to 6 inches above the ruler. To get these measurements, I took a reference plane or a little rolly table right under it, as you can see in the bottom photo. I put a ruler there and then pushed it down, got the approximate right answer, then click my mouse and let go. Then record the data. First, for the strain gauge sensitivity, first we want to find the sensitivity of the strain gauge. It's very important. That's really the whole idea. See how sensitive it is. Then we want to measure the distance to the reference plane. For the tip load bang stress equation based on mass on the beam, strain gauge voltage is, you need to remove the offset and then average it out to get a more accurate answer. Then the output of the strain gauge and the displacement have a linear relationship. You do this with a polyfit from the points that are added out. And we, in the end, got a sensitivity of 12,387 millimeters per volt, which is very close to the correct answer, or it's what is expected. Next, for the beam stiffness, we want to find the stiffness of the beam. It's very important to see how it reacts to loads and forces that we may give it in any context, engineering-wise. So small changes in displacement, changes in load and displacement are proportional. The displacement, again, measured, the load is from a measured mass of coins that we know, that we can either get from the US Mint, or we can just have a scale for it and we know the exact amount. This gives us the load and the measurements. There are 2 assumptions. The A, there's small displacement as in seen in the Euler-Bernoulli beam theory, and also there's a constant cross-sectional area. This just means that there's no weak spot on the thing. It's just always the same. Next, for the initial displacement excitation, I took a ruler, measured again with the reference down below, pushed it down 20 millimeters with a finger, put an intention so it's positive, and yeah, then let go, and then the ruler oscillate up and down. The voltage output, as you can see, it decreases over time. This shows even though there's no tape, there's still damping on the system. And if you go more to the right, you can see there's more and more noise or jagged going up and down. It doesn't look as uniform. So there's more noise, but there's also a mass and a stiffness to the ruler, because otherwise there would be no vibration. There would be no oscillation. So first, for the estimation parameters, there's 3 sets of data that we gathered for each case. I chose the best case for each one. There's no averaging out, just whichever one looks the best, which one seems like the best data. Either choosing a linear curve fit or decrement. Logarithmic decrement works better for a small little curve where the actual damping ratio is small. So first, to do that, you got to mark the peaks in the plot. So visually, I just found the ones that seem to have the least amount of noise, that follow the flow of it the best, the flow of the curve the best. Then you calculate the change from that, and then you get the damping ratio. You have the equations on the right, which you have the change first, which is the natural log of A of whatever, point of whatever spot, and then point of the next spot, a certain amount of oscillations later, which usually is just about 3 or 4 or 5 oscillations. And then from that, you can get the damping ratio. With no tape, it became 0.94% damping, which is, it's very underdamped. It's about 1% of a critically damped system. And it only, from the natural frequency of 14.667, it just barely decreased to 14.66, which is almost nothing. Next, looking at the spectrum analysis, according to the MATLAB documentation and to the Canvas sources, the FFT computes the discrete Fourier transform using a fast Fourier transform. This is an algorithm that gets the spectrum analysis. It calculates, for the voltage, the different frequencies where it happens a lot, pretty much. So you get the dominant frequencies, which is the natural frequency in mode 1 here. You can only go up to Nyquist frequency, but here you only see up to 300. Came out to 14.667. which is slightly different than the estimated / calculated of 14.97. However, this is within one frequency resolution, so it can be within that error, no problem. So you see small excitation from O2. Next, when you overlay the theoretical versus the calculated with the experimental, you can see there's more noise. The further along it goes over time, it gets smaller, there's more and more noise, so it becomes more and more inaccurate. However, towards the left, where there's a larger signal, it's decently accurate. Our variables here, we get MKC and F of t. F of t is 0, C becomes 2 zeta Wn, and K becomes Wn squared. The results show from this plot, as you see the equation below, those are the constants that were calculated to make that plot happen. The theoretical model, yeah, it's a bit off, but that's mostly due to the noise that just, as it gets so small, you cannot filter that out, or it's really hard to. Next, looking at impulse, again, quarter. The coin displaces the ruler, causes actually more than just mode 1, causes mode 1, 2, and 3. The oscillation, again, decreases over time because of damping. Again, shows as mass and stiffness, because otherwise there'd be no oscillation. From this, we can see, using the spectrum analysis, that there are three dominant frequencies at 14.7, 91, and 253. The theoretical or the calculated 14.9, 93, and 262. 14.9 is similar, but the 93 and 262 is most likely from just having more noise at a higher frequency, and just, even though it's a slight percentage difference, it's still bigger. Next, looking at the tapes, you have the duct tape and the carpet tape, about 3.5 inch tape length. This is the same for case one, where you displace it about 20 millimeters. Exact same way, measure it. The carpet tape is thicker, duct tape's thinner, so you got more and less damping because of that. So evaluation, we see the top plot here, no tape, middle plot, duct tape, and carpet tape. The no tape has 0.94% damping ratio. The duct tape has 1%, and the carpet tape has 1.4. Overall, they're quite similar. Thicker tape goes towards 0 quicker, as you can just visually see in the graph. But there's slight differences due to human error with the actual initial excitation based on how much I was pushing it down. So there's that too. In summary, they all have the same first natural frequency, measured natural frequency. The biggest error seems to be between case 1 and 2, where they should have the same damping ratio. There's no tape, but it's off by 0.06, which is small but noticeable in the calculation. The damping increases, excuse me, the damping increases with the tape. The duct tape doesn't seem to do much, but the carpet tape is a huge difference, which is interesting to note. In conclusion, the systems are all very underdamped, including the carpet tape. The noise increases the longer you go, and as the signal becomes smaller. The spectrum results show the first three natural frequencies. They represent how much the ruler is actually vibrating at. The dominant is the first mode. That's just what it's vibrating at from having a displacement. The second and third is from the environment when it gets an impulse, where it can actually have those three different frequencies. And here are these references. We have a couple of reports and the Canvas materials. Thank you, and have a good day. Bye.